Hello everyone, this is another video on atomic molecular phase where we'll be discussing gate PYQs. Okay, this is, next Saturday is your gate exam. So in this week we'll be discussing all the PYQs from all the papers. Alright, so don't worry. Stay tuned, we'll be discussing everything. Okay, so the first question is ground state electronic configuration, ground state electronic configuration of the rare earth ion Nd3 plus is PD 4F3 5S2 5P6. Okay, assuming LS coupling, the Landé-G factor, okay, of this ion is Landé factor of this ion is 8 by 11. Okay, the the effective magnitude. So the magnetic moment, effective magnetic moment in the units of Bohr magneton, mu b is how much? Okay, this is the question. Okay, so GATE 2019. Ground state electronic configuration of Nd3 plus is PD 483 5s2 5p6. Assuming LS coupling, the Landé factor of this ion is 8 by 11. Okay, the effective magnetic moment in units of Bohr magneton may be used. Okay, so let's write the ground state configuration first. Ground state configuration is what? Again, PD 4F3 5S2 5P6. Alright, so 4F3 will be configuring with respect to 4F3 because these are field orbitals. So 4F3 is the one that is not field. So here F has 7 boxes. 1, 2, 3, 4, 5, 6, 7. So -3, -2, -1, 0, 1, 2, 3. Okay. Yeah. So 4F3, 3. So 3 it will be packed with 3. Okay. All right. Is that right? This should be plus. The beginning ones are plus, these one are minus. So you can see in the L is what? Summation of ML. These are ML values. Summation of L will be plus 3 plus 2 plus 1, that will be 6. Okay. So L is your 6. Now L is your 6. Now this is what is S? S is this is half. This is half. This is half. S is your 3 by 2. Yeah. 3 halves, so 3 by 2. So what are the J? LS coupling will be there, right? So J will be L plus S to L minus S. Okay, J will be L plus S to N minus S. So L plus S is how much? 6 plus 3 by 2. 2. So 6 minus 3 by 2. So that is 15 by 2 by 2. That is 9 by 2, right? Yeah. That will be 15 by 2, 13 by 2, 11 by 2, and 9 by 2. Okay, so J value up to 9 by 2. So here we will do what? We'll take the minimum value. Let's take the minimum value. That is 9 by 2. Okay, so Your mu is what? Mu is Gj, mu b, j whole into j plus 1. That is your mu. So G value is 8 by 11 as given, Landagy factor 8 given in the question. Mu v into j whole into j plus 1, that is 9 by 2 whole into 9 by 2 plus 1. So 8 by 11 mu b, 9 by 2 into 11 by 2. Is that alright? Yeah. So 8 by 11 mu b, this will be 99 by 4 root over. If you calculate this thing, that will be 3.62 mu b. Okay. That is your what? That is your effective magnetic moment. 3.62 Bohr magneton. Write in terms of mu v, okay? Because it's question. The question is written the effective magnetic moment in units of Bohr magneton mu v. So we wrote it in case like in units of Bohr magneton mu v. Alright? Yeah. So this would be the answer. Yeah. Question number two. Question number two. Question number two says the spin orbit interaction term of an electron. Spin orbit interaction term of an electron moving in a central field, moving in a central field is written as is uh, Fr is equal to L dot S. uh, so if an electron moves, the electron moves inside a uniformly charged sphere, uniformly charged sphere, hmm, then options are option A, Fr is equal to constant, option B, Fr is proportional to R inverse, option C, Fr is proportional to R to the minus 2, option D, Fr is proportional to R minus 3. Okay, so this is your question. Spin-orbit interaction term of an electron moving in a central field is this, where R is what? R is the radial distance of an electron from the origin. Okay, if the electron moves inside a uniformly charged sphere, then Fr is equal to constant, Fr proportional to R inverse, Fr proportional to R minus 2, Fr proportional to R to the minus 3. So we have to solve this question. So how to solve this question? If you see, interaction energy is what is interaction energy or central potential? If you say the interaction. Okay, this is not equal. Okay, this is into. Yeah. So interaction energy U is equal to Fr as given L dot S. Yeah. Okay. Where for central potential, what is Fr? Fr is how much actually? Fr is 1 by R del V by del R. Okay. Fr is 1 by R del V by del R. So Fr is equal to 1 by R. Okay, what is for B? V is the potential of, this is what is in the question. If electron moves inside a uniformly charged sphere. So if we can calculate the potential of, okay, what is the potential? Potential of a uniformly charged sphere is how much? V is equal to KQ by 2R. Remember this formula, 3 minus R square by R square. kq by 2r whole into 3 minus r square by r square. So del by del r of kq by 2r 3 minus r square by r square. Yeah. So 1 by r. Now all this will come out. Kq by 2r del by del r of 3 minus r square by r square. Yeah. So kq by 2r, this is minus 2r by r square. R got cancelled, 2 got cancelled. So that will be minus kq by r cube. Okay? Minus kq by r cube. Alright, this is your FR. But if you see, this is not dependent on r. There is no dependence on r, small r. If you see, in the options it is asked what is the dependence on small r. But if you see, all the r, small r's are cancelled. So there is no dependence on r, right? No dependence on small r. So what can we say? We can say FR is constant. It's not changing with respect to r. Okay. So what will be the option for it? The option will be option A. Again, a very good question, but the thing is, you need to know these things. First of all, FR is how much? 1 by R del V by del R. This is FR. FR is 1 by R del V by del R. Now, what is del V by del R? What is V? V is, you here given electron is moving inside uniformly charged sphere. Electron is moving inside uniformly charged sphere. So, what is the potential inside a uniformly charged sphere? So, potential for a uniformly charged sphere is what? KQ by 2R 3 minus r square, 3 minus r square r square. So these things you need to remember to solve this question. See, here we are using electrostatics and atomic molecular together. So this can also be said as a electrostatics question. Okay, but you should be prepared to solve this kind of questions, like intermix questions. Okay? This one also from GATE 2019, 2 mark questions. Okay. Yeah. Next question, question number 3. Question number 3. Question number 3 will be an atom in its an atom in its singlet state. Atom in its singlet state is subjected to a magnetic field. Is subjected to a magnetic field. Is subjected to a magnetic field. Magnetic field. The Zeeman splitting of its 650 nanometer 650 nanometer spectral line is 0.03 nanometer. Yeah. The magnitude of the field is the magnitude of the field is magnitude of the field is how much? Okay, how much Tesla? That is the question. Options. This is a NAT numerical answer type question. Okay, it's a GATE 2018. An atom in its singlet state is subjected to a magnetic field. Zeeman splitting of its 650 nanometer spectral line. Zeeman splitting. It's Zeeman. Okay, is 0.03. If you remember what is singlet splitting, for singlet it is what? Normal Zeeman effect, isn't it? Normal Zeeman effect for singlet splitting. Hmm. Like del S is equal to 0 here. Yeah. So normal Zeeman effect, but that doesn't help us that much. Magnitude of the field. So P is asked. What is given here? What is given if you see? What is given? It's given. Lambda is given. Spectral line 650 nanometer. Zeeman splitting. Splitting means what's given? Can you tell me? Splitting means del lambda. Okay. Del lambda is 0.03 nanometer. Del lambda is your splitting, and lambda is your spectral line. Remember these things. Okay. So, if you can, what is the formula for it? What is the formula? Del lambda is equal to lambda square by c ev by 4 pi m. That is the formula. And I hope you remember this formula. It's very important. And we need to calculate b. So if I keep b in this side, everything to that side, 4 pi m c ev by lambda square. That will be your is it a, no, sorry, sorry. B is equal to everything that's a 4 pi m c del lambda by lambda square ev. Yeah, that will be the formula. So let's put everything. 4 pi into m is mass of electron 9.1 10 to the minus 31. C 3 into 10 to the power 8. Del lambda is given as splitting is 0.03 nanometers, 0.03 10 to the minus 9 whole divided by lambda square. Lambda is a 650 nanometer, 650 10 to the minus 9 whole square. E 1.6 10 to the minus 19. Okay, I'm sorry. B is what we have to calculate. So if you put all these values, you will get the answer in plus. Okay. This is again not hard, but the thing is you need to remember the formulas. Otherwise, it's not possible to solve these questions. Is that all right? Okay. We'll be writing the next question. That'll be question number 4, I think. Yeah, that'll be question number 4. So let's write the question number 4. 4 MeV gamma rays, 4 mega electron volt gamma rays. Okay. Emitted by emitted by emitted by the de-excitation emitted by the de-excitation of 9 F19, okay, are attributed uh, assuming assuming spherical symmetry assuming spherical symmetry, all right, to the transition of protons, to the transition of transition of protons, yeah, from 1D 3 by 2 state, hmm, to 1D 5 by 2 state, 1D 5 by 2 state. Yeah, if the contribution of spin or return, I hope you're writing the question along with me. Write the question. Don't only to solve the answer, because writing the question and then solve the answer, it's a process. It's a classic age-old method, and it's there for a reason. The reason is while writing the question fits in your brain. Like if we just see the PDF, like if I just print the that page of the PDF and then solve it, then it won't be that effective as compared to writing the question and then solve it. Okay, you will feel it. The magnitude of C is the writing of the question, seeing it in your own, like, yeah. So it's a different kind of thing. You'll be saying, but sir, there is no question. We don't have to write question in exam. But see, this is a practice time, so you should remember the questions also. Hmm. 4 MeV gamma rays emitted. Again, now the trick, no, not the trick. Now the thing is to read the question 2 times at least before approaching it. Read the question just blankly, whatever. Just read it, process it a bit slowly. 4 MeV gamma rays emitted by the de-excitation of fluorine 19 are attributed. assuming spherical symmetry to the transition of protons from 1d 3y2 state to 1d 5y2 state. Okay, there is a transition of protons from 1d 3y2 to 1d 5y2. If the contribution of spin orbit term to the total energy is written as CL dot S, the magnitude of C is. Okay, so what we got here? The thing is, the transition is from 1d 3 by 2 to 1d 5 by 2, right? Is that right? Transition is from 1d 3 by 2 to 1d 5 by 2. So from here we can write. What can we write from here? We can write J is equal to J1. This is J1 is equal to 3 by 2. And J2 we can write as 5 by 2. Is that right? Yeah. Okay. So we know SPDF, right? SPDF and SPDF. So S for S is 0, 1, 2. So D is here. L is L1 is 2. S1 is half. Yeah. L2 is also 2. S2 is half. So from here we have got our 3 by 2 and 5 by 2. Right. And because 2 and half, if they like mix with each other, that will be giving me 3 by 2 5 by 2. That's what I'm getting here. All right. So now what do we know? We know the LS coupling as J is equal to L plus S. Is that right? So I will take the square on both sides. So that will be L plus S whole square. That will be L square plus S square plus 2LS. Okay. J square is equal to L square plus S square plus 2LS. So that will be giving me J square minus L square minus S square is equal to 2LS. Yeah. So L dot S is equal to J square minus L square by minus L square by 2. Yeah, is that alright? Now J square is J whole into J plus 1 minus L whole into L plus 1 minus S whole into S plus 1 whole divided by 2, and there should be an H cut square. Is that alright? Now the question is what? The question is Now the question is contribution of the spin orbit term to the total energy is C dash. So contribution is written as what? This is 1d 3 by 2 to 1d 5 by 2. Alright. So the contribution I can write as del E is equal to uh, alpha L dot S for 5 by 2 minus L dot S for 3 by 2. Is that right? This is as you practice more you will understand this is the one. Okay, alpha L dot S for that will be, see, L and S are common for both, isn't it? L and S are common for both, so they will be eventually subtracted. So what will I do? Only J is different for both of them. So I'll just subtract the J values, like J whole into J plus 1. So 5 by 2 whole into 5 by 2 plus 1 minus L is a 3 by 2 whole into 3 by 2 plus 1. Is that right? Yeah. So if I do it now, that will be alpha 5 by 2 into 7 by 2 minus 3 by 2 into 5 by 2. Is that right? Okay. So alpha that will be 35 by 4 minus 15 by 4. Yeah. So the alpha 20 by 4. So that will be giving me 5 alpha. Okay. Is that right? 5 alpha. Or did I do any mistake? Please let me know if I have done any mistake. Okay, I get it. There is 1 by 2 here. This 1 by 2 is also should be there, right? No, it should come here actually. Yeah. Yeah. So that will be 20 by 8. 20 by 8 alpha. That will be your what? Yeah, delhi is equal to 20 by 8 alpha. Okay, 20 by 8 alpha, which is in fact your C L dot S, and alpha is actually C here. Okay, so don't worry about it. So L dot S is your, like this thing, this term we're getting as 20 by 8. Sorry. My bad. What I'm doing. Yeah, 20 by 8. No, it's correct. It's correct. I'm sorry. 20 by 8 C. Okay, but in the question, if you see, what is the value of the energy? 4 MeV emitted by the de-excitation. So this energy has helped in de-excitation of proton from this state to this state. That means the energy in this state, like the energy in splitting of the state, will be equal to this energy, isn't it? So that means del E. This del E, whatever we got as 20 by 8 alpha, C or something, or alpha whatever, that should be equal to your what 4 MeV, isn't that right? Yeah, 4 MeV. So C value will be how much? C value will be 32 by 20. Okay, 32 by 20 MeV. So if you calculate it, that would be um, 16 by 10. That means 1.6 MeV. Yeah? So C value is 1.6 MeV. That's the answer. Okay, that's what the answer is. And yeah, I hope I understood this question. This is easy. Okay, this is easy actually. It's just that you need practice more in this topic. Okay. Okay. All right. So this was your question number 4. Next comes your question number 5. Question number 5. Okay. The Thom symbol for the electronic ground state, for the electronic ground state of oxygen atom is oxygen atom is the Thom symbol for the electronic ground state of oxygen atom is. Options are 1 is 0, option B 1d2, option C 3p0, option D is 3p2. Okay, so oxygen, this is also GATE 2018. Okay, so oxygen, right? Oxygen means what? 1 is 2, oxygen atomic number is 8, 1 is to 2 is to 2p4, isn't it? So 2p p is the one that is not complete. So plus 1, 0, minus 1. So here this 3 now. One more is left. So, okay. These are ml values. So L will be what? L is a summation of ml. That is, this is plus 1 into plus 1, that is plus 2 plus 0 minus 1. You got it right how this calculation is done. This is plus 1. So two things, two electrons. So plus 2 plus 0 minus 1. This ml values. So this one be L will be your 1. Okay. L will be 1. Now what is the S value? Okay. S will be what? This is your half upward. This is minus half, half, half. So these two are cancelled. What is left? 1. So S is the 1. So if we do the LS coupling, here J values will be L plus S to L minus S, right? So 1 plus 1, 2, 1 minus 1. That is 2, 1, 0. These are the J values. Okay. And we know L values are what? L is 1. S is 1. S is 1 means 2S plus 1 is 3. So I can write it as 3 for L1. It is P, isn't it? Because we know SPDF. So L is 0, 1, 2. So for 1, it's P. So 3P, and the values are 2, 1, 0. Okay, now there are three terms now. So which term is the ground state energy? See here. See what is happening here. This orbital is more than half filled, isn't it? More than half. Half means 3 for P. So it's more than half filled. So for more than half filled, what happens? For more than half filled, highest J will have the lowest energy. Is that clear? So highest J means, what is highest J? 2. 3p2. So 3p2. You can also write for less than half filled, more than half filled. For less than half filled, lowest j. See, less means lowest, more means highest. Like that, remember. Lowest j will have lowest. For less, everything is low. Lowest energy. Okay, for example, this was like this. Okay, then it will have been 3p naught, 3p0. Why? Because this is less than half filled, so the lowest j term would have the lowest energy. Okay, yeah. Alright. This is Horn's rule. I hope you have studied this. I have also done it in one of my sessions, so you can check that out in our playlist. Okay. Okay. Next question. Question number question number six. We'll solve 10 questions at least. That is our challenge for this class. Six. Okay. Which one of the following is an? Which one of the following is an allowed electric dipole? Is an allowed electric dipole transition? Is an allowed electric dipole transition. Okay, so 1 is 0 2, 3 is 1, 2p 3 by 2 2, 2d 5 by 2, 2d 5 by 2 2, 2p half, and option D is 3p 0 to 5d 0. So try this question first, then I will solve it. Which one of the following is an allowed electric dipole transition? Okay, how to do it? See, for electric, what is the condition for electric dipole transition? We should know that. For electric dipole transition, what is the del L is equal to 0 plus or minus 1. Yeah, but 0 to 0 is not allowed. 0 to 0 is not allowed. Del J is equal to 0 plus or minus 1. Yeah, and del S is equal to 0. This is the condition. So you have to check which condition is which of the options is working. First one here, if you see, uh, okay, here, see, your del S must be 0, right? Here, if you see, this is S, 2s plus 1 is equal to 1. So S is actually half. Here, 2s plus 1 is equal to 3. So S is actually 1. So half to 1. So this is not possible because del S is not 0 here. Got it? So this is not the answer. Now this one. Here del S is same 2 2. So this is correct. Del S is 0. And del J 0 plus minus 1. Yeah, 0 plus minus it's coming. It's 1 or minus 1, whatever. Del L is 0 plus minus 1. Yeah. Because P is your, for P L is 1. For D L is 2. So it's 1. So yeah, this condition is satisfying. Let's see other options. This one. Del J. If you see del J is not, it's 5 by 2 minus 1 by 2 is actually 2. 4 by 2 that is 2. Del J is not, cannot be 2. So this is wrong. Now this one. 3 to 5. See, S values are not same. Even though J values are same and the del L value is plus or minus 1. But here S value is 3 to 5. 3 to 5 S is not possible. Del S must be 0. That is wrong. Okay, so the option is this. Got it? For di- electric dipole condition, these are the conditions. Again, write, you can write it again. Write it again and again so that for electric, it's not hard to remember even the selection rules. It's almost same. For electric dipole transition, okay, del L is equal to 0 plus or minus 1, del S is equal to 0, del J is equal to 0 plus or minus 1. Okay, next question. This is your question number 6. Question number 7. Okay. Question number 7. The intrinsic permanent, the intrinsic or permanent electric dipole moment, intrinsic or permanent electric dipole moment in the ground state of in the ground state of hydrogen atom, in the ground state of hydrogen atom is dash where A naught is the Bohr radius, where A naught is the Bohr radius. So option A is minus 3 E A naught, option B 0, option C E A naught, option D 3 E A naught. The intrinsic permanent electric dipole moment in the ground state of hydrogen atom is how much? Okay. The intrinsic permanent electric dipole moment in the ground state of hydrogen atom is how much? Try. Okay. What is your dipole moment energy? Dipole moment energy is how much? Minus EER cos theta. Okay. So for intrinsic permanent dipole E1, I have to write as minus average of ER cos theta. Okay. That means EE into average of R into average of cos theta. And average of cos theta is what? 0. Average of cos theta is 0. Why? Because this is the graph of cos theta. Okay. So this is plus, plus, minus. So the average, if we take this will be adding to this. So the average will be 0. Yeah. Plus, plus, minus 0. So the answer will be 0. So the dipole intrinsic permanent dipole will be 0 for the hydrogen atom. Okay, alright. So question number 7. Question number 8. The expression for the second overtone frequency, the second overtone frequency, the vibrational, the vibrational absorption spectrum, the vibrational absorption spectrum of a diatomic molecule, diatomic molecule. Okay, in terms of harmonic frequency, omega e and anharmonicity constant, anharmonicity constant chi e is The options are 2 omega e 1 minus chi e. Option B 2 omega e 1 minus 3 chi e. Option C 3 omega e 1 minus 2 chi e. Option D 3 omega e 1 minus 4 chi e. So these are the options. The expression for the second overtone frequency in the vibrational absorption spectrum of a diatomic molecule in terms of harmonic frequency omega e and uh, so second overtone frequency. So second overtone, if I just revise this topic a bit, if I revise it a bit, see, fundamental band is what? What is fundamental band? One having v is equal to 0 to 1. That is a fundamental. First fundamental band. So first overtone is what? First overtone is where v is equal to 0 to 2. That is the first overtone. Okay. Second overtone is what? Second overtone is 0 to 3. Yeah. Second overtone is your what? 0 to 3. Okay. Second fundamental, if I say second fundamental is your 1 to 2. Okay. This is also called a hot band. Okay. So, 0 to 1, 0 to, so we need what? Second overtone as in the question. It's talking about second overtone frequency. So, second overtone, let's do it. We know the formula first of all. Formula we know, right? Formula is this is a wave number in terms of frequency, like a wave number. That is v plus half omega e minus v plus half square omega e chi e. So for v is equal to 0, that will be half omega e minus 1 by 4 omega e chi e. V is equal to 3, that will be 7 by 2 omega e minus 49 by 4 omega e chi e. Yeah. Right. So Delhi will be what? 6 by 2, that is 3 omega e minus 49 minus 1, 48 minus by 4, that is 12. 12 omega e chi. So if I take 3 omega e constant 1 minus 4 chi, that will be the answer. If we check the options, option D will be the correct answer. Okay, option D will be the correct answer. Okay, so this was the question number 8. Okay, question number 9. Positronium is an atom. Positronium is an atom made of an electron and a positron. Okay. Given the given the Bohr radius given the Bohr radius for the ground state of for the ground state of the hydrogen atom, okay, to be 0.53 angstrom. The Bohr radius for the Bohr radius for the ground state of Bohr radius for the ground state of positronium is positronium is Positron is an atom made of an electron and a positron. Given the Bohr radius for the ground state of an hydrogen atom to be this. Bohr radius of the ground state of positron is atom made of electron positron. Bohr radius for the ground state is given A naught is equal to or R naught whatever 0.53 angstrom. Is that right? So uh, the Bohr radius for the ground state of positronium is asked. So see when we talked about another atom or another atom except hydrogen, okay, the formula will be Rn. Okay. Now, Rn will be A naught Me by mu. Where mu is the what? Mu is the reduced mass of that atom. Reduced mass of that atom. Here the atom is positron, so the reduced mass of positron will be there. Reduced mass of positron will be Me into Me divided by Me plus Me because mass of electron and positron are the same because they are particle and antiparticle. A particle antiparticle pair has the same mass but opposite charge. That's the difference. Same mass but opposite charge. Okay. So Me by that will be giving me Me by 2, right? Me by 2. So I'll just put it here. So Rn is equal to A naught Me divided by Me by 2. 2 will go up, Me will be cancelled. So 2 A naught. 2 A naught will be how much? What is A naught? A naught is given 0.53 angstrom, 1.06 angstrom. Is that right? Is that alright? No? So this is how you solve these questions. Okay, just remember the formula. Don't forget it. Please don't forget these formulas, okay? Okay, next question. It's question number 9. Question number 10. This is a good one. Let's end with a good one. The number of permitted transitions. The number of permitted transitions from 2p 3 by 2 to 2s half in the presence of a weak magnetic field. In the presence of a weak magnetic field is what? Yeah, yeah. Number of permitted transitions from 2 p3 by 2 to 2s half in the presence of a weak magnetic field is how much? Okay, so where we have to do here, we have to draw this. Like let's do 2p3 by 2. That means what? 3 by 2. So 3 by 2 can be split into what? 3 by 2, 1 by 2, minus 1 by 2, minus 3 by 2. So let's do it. This is 3 by 2, 1 by 2, minus 3 by 2 is 1, minus 1 by 2. Yeah. Now 2 is half, right? Half can be into more. Plus half and minus half. 2 is half, plus half, and minus half. But we need to know the selection rule, right? Selection rule for Riemann transitions. Example what? Selection rule. Selection rule for Riemann transitions. Selection rule is what? Del mj 0 plus or minus 1. Okay, where 0 to 0 is not allowed. If j is equal to 0. Okay. So let's do 0 plus or minus 1. Let's do it. Same, not allowed, only different. So this is not allowed. This can be allowed because this is giving minus 1. Okay, this is not allowed. Okay, minus half plus half. Yeah, this is minus 1 allowed. This is 0 allowed. Okay, half to half is allowed. Half to minus half is also allowed. Yeah, 3 by 2 to half is allowed because it's giving me 1. 3 by 2 to minus half is not allowed, it's giving me 2. So 1, 2, 3, 4, 5, 6. So 6 lines. So there are what? 6 lines, total 6 transition lines. Okay, that will be the answer. So the answer will be 6. Is that alright? Okay. Write one homework. Number 11. Question is the excitation wavelength of laser in a Raman effect in a Raman effect experiment is 546 nanometer. If the Stokes line if the Stokes line is observed at if the Stokes line is observed at 552 nanometer, okay, then the wave number of the anti-Stokes line anti-Stokes line in terms in centimeter inverse is. Okay, this is the question. Excitation, this is a NAT type question, numerical answer type indeed. The excitation wavelength of laser in a Raman effect experiment is 546 nanometer. The Stokes line is observed at 552 nanometer. Then the wave number of the anti-Stokes line is X. That will be the question. Okay. So yeah, I hope you understood this class. If you didn't understand at any point, please let me know in the comment section. Okay, we'll be solving more and we'll be doing all the PYQs before GIT. Okay, so don't worry. Okay, stay tuned. Thank you very much.